Okay. Today, we're just going to do a little tinkering and maybe get started on some compressed sensing. See how it goes. All right, so there's this threshold mask for the support value. We're going to call it support threshold. I don't actually know if it can be 0. I don't think it can. Oh, we've already got threshold mask as an input. Okay, so we're just going to change this to support thresh because that name makes more sense to me. Okay. And now, if we call pisco, you get this. Oh, no. Okay, so, I'm honestly a little confused right now. Okay, and what if I set it to 0.3? Does the support get smaller or larger? Same size? That doesn't make sense, does it? Same size. That doesn't make sense. Oh, boy. Oh, it's because when I don't supply it, okay. There we go. Okay. Okay, so with a support threshold of 0.05, the support's small, and this does not include all of the leg, obviously, because the leg extends up all the way to the top of the image. And then what if we send this to a large value like 0.3? Now it does go all the way to the top of the image, which indicates that it might actually the support might actually encompass all of the support of the image. Okay, so we needed a large support here, right? And even though there's leg there, of course, I'm not, it's hard to see. It's not very significant intensity. Now here's what I'm wondering. Dear streamers, you know what I forgot to do? I forgot to tell my massive audience that I'm currently streaming. Okay. So we're going to do this stuff. Let's not do SPIRiT. Let's do model-based reconstruction. Let's just try that because it's fast. So this is truth. Now my question is, can I call Pisco with all the data? This returns, so I guess all the data would be BSX times SMAPS times image, where image is the reconstructed image, image MBR. What if I made the threshold support thresh much smaller now? That doesn't seem right. So these are the sensitivity maps that show up with all the data. So does Pisco assume that the auto-calibration region is small? Okay, if that's the case, what if we cropped it to double the size? The size of the left is 39 by 39 by 8, and the size of the right is 38 by 38 by 8. Does Pisco assume that the ACR is odd or something? So it's just getting the whole support now. I don't understand. Oh, that was silly. I got to take the FFT too. Okay, so we're going to put this into the code so that we could play with it there. So here's my contention, right? What I'm wondering is, we could call this the augmented K samples. Let's call it the augmented ACR. Okay. Well, K samples augmented is equal to, now we're going to have to do an IFT shift. No, sorry. Okay. We're going to have to do an IFFT shift 2. Followed by an FFT2 followed by an FFT shift 2. These are the K samples augmented. This is the ACR augmented. Now my question is, so what's happening here is that we're doing a reconstruction. We're looking at the model-based reconstruction. And now so this is interpolating missing Fourier data, right? Okay. Well, okay, and I think this FFT2 was the issue before. So let's send all the data into Pisco for the second run. That's model-based, that's the result of model-based reconstruction. Now what's the support 2? Okay, that's really bad, but you see all this noise? Is that the reason why? So we're going to move this. We're not going to do model-based reconstruction. We're going to do recon SPIRiT reg, which hopefully gives a better answer than model-based reconstruction. So the default threshold for support thresh, the threshold value for support thresh is 0.3. I'm reducing it a lot, which I think increases, like reduces the percentage of eigenvalues that are retained or something. Image MBR doesn't exist. We'll open this up so that if we have to run a long time again, we'll start working on compressed sensing. All right, what does that support look like now? Okay. Huh. What if we set the threshold to 0.1? That didn't change much, did it? You see, there is stuff. There is stuff outside of the support, isn't there? I think. Um, so this should just show what's outside of the support. And there is some stuff there. Not much, but some. And what if I set this threshold to 0.3 now? Okay, that's looking promising. Now there's really nothing outside of that support, is there? Okay. So it turns out I like the threshold of 0.3. I think that's the default threshold that I have. We can even, our sample mask is equal to 1 is equal to k data. Our sample mask is equal to 1 or is equal to k samples. What's the size of sample mask? It's just two-dimensional. Okay. So this is me replacing, like, it could be the case that, well, we have a data consistency constraint, don't we? Yeah, I don't know that that's a good idea. Maybe it is. Let's find out. Same. Yeah, same. I think that's because of the data consistency constraint. We don't need to do this. So we've got these augmented data. Or these are the original, the estimated Fourier values at all frequencies. We can call Pisco on that. We don't need those sensitivity maps. It gives us a new support. And then I'm thinking we can run this again. You see. And that should do better. This is basically made possible because Pisco is so fast. Let's see what the difference is between these two reconstructions. How do they look? This is Spirit Gam. This is Spirit Gam 2. Spirit Gam looks better, I think. Now, why is that? The estimate of the support is much better, I would say. Oh, but it doesn't actually go to the top. Maybe there's something there. I would say the estimate of the support is better. And good. I would say it's very good. And the only difference between Spirit Gam and Spirit Gam 2 is the estimate of the support. Now here's a question. Am I right that it's better? So that's very noisy in this area, Spirit Gam 2. How about Spirit Gam? Yeah, Spirit Gam is better. Why is that? That's strange. I got here and I got here. That's good to know. We'll keep this around. Maybe something will resolve and this will start to work out. I made the threshold 0.4. Let's see how that goes. Right now I'm storing SMAPs and support, but I don't have to because piece goes just so fast. Especially when we're just using the auto calibration region. Watch. Oh, that didn't. Okay, let's do it again. Watch. Boom. Oh, that was the ACR. Boom. Piece goes so fast. So now the support's very large. We'll have to see if this is the threshold that we like in the end, whether it even benefits other anatomies, like the brain. Does it actually reduce the overall image or not? Is the support a subset, a strict subset of the field of view or not? And if so, by how much? Enough to matter? Spirit gamma, truth. It's noisier. That's pretty good. I'd say that's real good. They're not great. This is, 1/6 of the data or something. Not a whole lot of data to work with. It's kind of a miracle it performs this well. Here's gamma 2. That's interesting. So what's support 2? Support 2. So the support's much smaller, and I like that support. Here's spirit gamma. Here's spirit gamma 2. Spirit gamma's a little better. That's so strange. The only difference between the call to spirit gam and spirit and the spirit the only difference between the call to recon spirit reg that generates spirit gam and spirit gam 2 is the support. That's the only thing that's different. Everything else is the same. We don't overwrite the S maps. W size is the same. SACR is the same. K samples is the same. As long as we're hacking and tinkering, let's see what happens if we just use twice the ACR after the first reconstruction. But of course, now that now there are two differences. What is the ACR used for in Spirit Reg? Find W. Okay, that's all it's used for. It's find W. This support is much less than this. And it seems much better. So everything tells me, since we're giving it more information, there's more of a restriction. We only reconstruct the image where the support is white. So since we have to reconstruct less of an area here than we do over here, and we have the same amount of data, seems like we should just get a better image out. I'm very surprised that we don't. Now in this case, we used twice the HCR, which was a total hack, and That turned out to be a terrible idea. So let's not do that. Well, that didn't work as I had hoped. This is FSX. I'm not sure why it didn't work. That didn't work. I'm going to have to stew on that a while. Okay, now let's try some compressed sensing. So the problem we're going to solve is what should we call this, huh? We got any Greek letters left? Beta? Zeta? Phi? Rho? Lots of Greek letters left. Okay, we're going to go with zeta. So if you supply zeta, nope, because we're going to calculate zeta. And the SPIRiT regularization. Oh boy. We're getting an A passed in here. FS, MFS, WMIFS. So A does MFS and WMIFS, which we're going to need, right? We're going to need MFS PT W minus IFS. Now here's a question. And apply A. Where is it? Where does apply A get used? Right now it gets used at minimization over a sphere in Tikhonov. So for Tikhonov, where's the P? Right? That's what I'm wondering. Does apply A have P in it? Oh, okay, yes. I see. Okay. We're going to need that, and we're going to need that. And we're also going to need that for this one. So we're going to keep A, and it's going to be defined just how it is. We will also use some form of PDHD to solve this problem. And so we can even copy this code here. All right, we got the start, we got the end. Now, if we just had these lines in the middle of the code, we would be done. Okay. Where's B? K data. Just keep copying code. F is the same. It's not included in this problem, so we're just going to set it to 0. Therefore, the proximal operator of F is just the identity matrix. These things are going to change. In particular, G is going to take 3 arguments. Okay, so this is going to be the third function. Indicator that divided by num LB is less or equal to zeta. So we've got this, that's here. We've got this, that's here. The last part is this. We don't use the 1/2 with the psi. Okay, norm. N1, 1. If we're going to use that notation, then G1 is different. That's G1. And now the proximal operator is simple. Dead simple. Let's give this a default value for threshold. Of 1. Now I don't have to provide it there. Okay, so that's G1 and its proximal operator. Now we need the conjugate. Well, we'll do the conjugate later. G2 is equal to, I think we've already got this somewhere, perhaps a minimization over a sphere. Yep, that looks like G2 to me. Good thing too, because I mislabeled it as B2. Call this NV. Do I have the proximal operator of G2? Sure looks like it. This is a bunch of projections, right? Yep. Wait a second. Wait, so my G2. Yep. Now I've got G2 and prox G2. Now I need G3. And that one we don't have. Okay, indicator of this. It's going to be a similar indicator function. Wait. These are reversed from this. So this is actually G3. This is G3, and what I'm making here is G2. Okay. Now this totally not correct, right? That's G2. Except we don't have to iterate over coils, do we? So we don't need this. Into minus b, norm squared divided by mb is greater than zeta, out to infinity. Otherwise out is 0, and we don't even need the reshape. So G2 could have been much simpler. Now we need the prox of G2. For the prox of G2, note that G2 of into is equal to indicator the norm of into minus b. Let's do it like this. Less than or equal to square root of zeta. So you know this less than or equal to zeta. Take the square root of both sides. You have the norm not squared divided by the square root of nb is less than or equal to the square root of zeta. And so this is going to be square root of nb times square root of zeta. It's an indicator function for that. Why does that matter? Because now I know that I just need to project its argument onto a ball. Prox G2 at in project onto ball into minus b, a ball of radius square root of mb times square root of zeta, and then add b after. I'm going to call this ball radius. If we were doing this once, wouldn't matter, right? But I think this happens every iteration of PDHG, and maybe multiple times in each iteration because of the line search. Okay, I think we've got G2 and prox G2. Oh, there's a ball radius here too, shoot. call this square root NB square root zeta. Shouldn't be any name conflicts there. Just to be sure, what's the proximal operator of the L2 norm? Oh, I've been making mistakes, haven't I? We need in T, which makes this T. That's fine. Because we don't need the proximal operator of G2, but a scaled G2, scaled by T. So if F is the L2 norm, scaled by T, I'll bet you I got it in fork lib. Prox L2. Sure enough. Okay. It's not the prox of L2. We've been through this before. It's the proximal operator of the indicator function of an L2 norm. And that is a projection onto a ball, as I've said so many times. XRP. Put 2 there, why not? Should I make the default radius for this 1? Okay, we've almost been at an hour. Prox G3. Now if we come back down to minimization over sphere, it's prox G1, then we got this prox G thing. Because G is equal to G1 plus G2 plus G3. So prox G, which one's G1? That's a product of S image. Is there an S image in here? No, let's change that. But there is an NPix, and that's really what I need. Right, because G1 is the L1 norm. We take the L1 norm of the pixels in an image, right? G2 is data consistency. So that's going to be n samples. That does not go to end, but it goes to plus n, let's see, so G2, indicator function is n samples. Right. NPix, oh, it's NPix plus 1 to n samples. NPix plus n samples. And then in3 is equal to in NPix plus n samples plus what's G3? NK data. Of course, this could just go to end. Oh. Oh, this could just go down. But it would be that plus NK data. Let's do that. Okay. We've got the prox G. We've got prox F. We don't have prox G conjugate, do we? Let's change that. Okay. And we're on our way to implementing a rather sophisticated, well, an addition of compressed sensing. I think that's where I'm going to end today. Next time we'll work on this apply A, which isn't the apply the A that comes in here. We're going to need like an apply A CS. So that's what we'll do next time. Thank you for your attention.